Hello everyone, I'm Sebastian Herold from Karlstad University in Sweden, and in this short presentation I'd like to show you some results regarding a study on the association between architectural smelts and degradation. So what is this about? Well, obviously it's about architectural smelts, which is defined as commonly used architectural decisions that impact system quality in a negative way, are not always used intentionally, of course. And the second thing is architecture degradation, which is the continuous divergence between the intended or prescriptive architecture and the as implemented or descriptive architecture, with all negative effects involved, like a reduction in the maintainability of the system, for example, because you don't have the desired structures implemented in your system. So why is that interesting? Common folklore says that architectural smelts lead or contribute to degradation, or that avoiding smelts avoid degradation. Studies saying this are in the majority. A bit of work also says there is no direct relationship. No matter on which side you are, empirical evidence for either statement is actually very scarce. And why is it interesting to know more about the association? Well, first of all, it's always fun to provide some empirical evidence for folklore, either for or against it. But also if there is no association, then this is very attractive from a degradation standpoint, because usually if you don't have an intended architecture, you have to go through architectural recovery to recover the intended architecture and to find out whether there is divergence at all between what you intended to do and what you actually did. So in a nutshell, the motivating question is, what is the association between architectural smelts and degradation really like? To keep the scope of the study manageable, we reduced the scope of the question a little bit. First of all, we look at three types of architectural smelts only: cyclic dependencies, hub-like dependencies, and unstable dependencies. And on the degradation side of things, we focus on intended module structures. So approaches that define what modules are to be expected in a system, what dependencies are allowed and desired, and where are the violations of these dependencies. The research question boils then down to, are the contribution to any of the three types of smelts and the classification as architectural violation dependent properties of dependencies in the source code? Can we say things like, if you have a dependency between two classes, which is an architectural violation, is it likely that at the same time it contributes to some form of smell? The system on the study was JabRef, which is a reference manager written in Java. Maybe some of you are using it even. It has a few interesting properties. First of all, it's not too small, which is important to find degradation and smelts at all, but it's also not too big for an initial study where you might want to dig deeper into the findings. It has a reasonably long history, which means that it's likely to find degradation. I think it came to life in 2003, and the version we looked at is from 2016. And the best thing about it is that we actually have an intended architecture available, which is rare. We don't only have it available, but it's also validated by the project team. What we did then was to take JabRef and to feed it to Arcan, which is a smell detection tool developed at the University of Milano. Arcan has a nice feature, and that is it converts the results into a Neo4j graph database. This means the identified smelts and the dependencies between classes are formalized as a graph. The second step, we took a tool called JITEC, which implements the so-called reflection modeling approach to architecture consistency checking. It results in a model which depicts the intended architecture as well as the dependency violations in the system. We adapted the tool in a way that it complemented the Neo4j database created by Arcan by edges representing violations. You can see one here. This graph was queried to fill in contingency tables, saying how many dependencies are in the system, how many dependencies are violations and contributing to smelts at the same time, or are just violations not contributing to smelts, and so on and so forth. If you know Neo4j, you know that you can use the built-in query language cipher, and you will notice that the text here, this is a cipher query asking for all dependencies that are violations and which are at the same time part of a cyclic dependency. These tables then were input for statistical testing, or more precisely for the chi-square test for independence between two properties. This table shows a lot of numbers, which are essentially the results of the testing, and the interesting rows, or first of all, I should say here, the rows are of the contingency tables are non-smelly versus smelly dependency, or numbers of frequencies of those dependencies. And the column in each table are non-violating versus violating dependencies. And if you do the testing for the tables, you will come up with the following results. For cyclic dependencies and unstable dependencies, we get statistically significant results saying there is some form of dependence between violations and the smells. But the phi values say that this effect is relatively small. These values tell you that it's roughly twice as probable to find violations among the dependencies contributing to smelts than in the rest of the system. And interestingly, we looked at something else, namely when toying around with Neo4j, we noticed that dependencies being part of cycles at most with 5 classes were never violations. So we looked at cyclic dependencies with more than 5 classes and more than 15 classes and found out that it's even more likely to find violations among them than in the rest, than in the other smells. So concludingly, we summarized this in 4 findings. The finding 1 is that the results provided evidence for dependency violations overlap with the cyclic dependencies and unstable dependencies. Violations were about twice as common in these smells. The second finding is that the effect size, though, is too small to say that degradation is mainly caused by smells. Avoiding smells might avoid some violations, but far from completely. The third finding is that the risk for violations in cyclic dependencies increases with the cycle size, and that small cycles seem to hardly contain violations at all. The fourth finding is related to the hub-like dependencies, where we didn't find any evidence that they are related to dependency violations, or as we state here, that hub-like dependencies become hubs for dependency violations. Hub-like dependencies are classes that have a lot of incoming and outgoing dependencies, and there is no sign that the number of violations increases dramatically with this kind of classes. Concludingly, architectural smelts and degradation seem to overlap partially, but not all types of smell are equally relevant for degradation. The results also suggest to treat primarily large cycles and unstable dependencies if your goal is to remedy degradation. In the future work, we would like, of course, to extend this type of study because we only had to look at 1 system and 3 types of smell, and we would like to increase both numbers to have findings with greater external validity. And the overall goal of this is, of course, to characterize the association between these 2 phenomena in more detail and to develop better methods against architecture degradation. So that was a very quick presentation. Thank you for watching, and if you have questions, then yeah, let me know. Thank you.